So welcome back to the second lecture of cable and suspension bridges. In the previous lecture we have seen the following: how much is the H, horizontal thrust, what is the tension in the cable, this formula WL by 2 root 1 plus L square by 16H square, and we have seen the tension H, the H, horizontal thrust in the cable. If you know the tension in the cable, horizontal thrust at the end, if the tension in the cable and the angle, if you know that H is equal to T cos theta. Yeah, and the maximum you will get at the end, and at the dip, at the center, theta is equal to 0. So you will get T minimum, the H minimum, which is T minimum, which is equal to H. Yeah, maximum T max will be at, maximum tension will be occur at the end, which is T max is WL by 2 root 1 plus L square by 16H. And another one is the, which we know that already from the arches and the parabola, y is equal to 4hx by L square into L minus x. And finally the length of the cable S, length of the cable, because the cable will be in parabolic shape, that the parabolic shape length L plus 8 by 3 h square, because this length of the cable is important because it plays a role in the economical situation, because length of the cable increases, the cost of the the cable and suspension bridge also gets increased. So that length is the whole cable is of great importance. Yeah, now look at the figure. Let's talk about the tower. You can see that its cable, it goes, main cable it goes, and another tower will be there, it goes over this one. Let us take one support actually. That is the TS is the tension in this cable here, and the main cable TS, and the tension in the anchoring cable is TA, and the horizontal thrust is H, and the vertical reaction VA. Let's say that is the height of the tower is H. And let us say this main cable makes an angle theta S with the tower, and anchoring cable makes an angle theta A with the tower. So you see, this tension in this cable, main cable, and tension in the anchor should be same. No doubt in that for equilibrium. Yeah. And the horizontal component, that is H, will create a horizontal thrust here on the tower, and this reaction, it will create a vertical force. The total load is transferred to the cable, and cable runs over the pulley. There will be a pulley over this one which is fixed on the tower. So there will be vertical reaction on the tower also. So our interest is how much is the horizontal thrust applied on the tower, because so that we need to design the tower also. For example, whether it is capable of taking this much horizontal thrust, is it capable of taking the vertical load also. You see, it comes like this actually. So this, as we discussed, TS, main cable tension and anchor cable tension should be equal. So the vertical reaction at the top of the tower is equal to, see, being theta S and the vertical one is T cos theta S. This will create T cos theta acting downward. T cos theta A, this is also acting downward. So net vertical reaction at the top of the tower is equal to T cos theta S plus T cos theta A. Please note this one. And similarly, horizontal reaction at top of the tower, horizontal thrust on the top of the tower. This is the horizontal component of theta A and theta. This will be TA. Because TS and TA being same, T sin theta S or sin theta S, which is horizontal, and because both are acting in opposite directions. See this one, Ts sin theta S, TA or T sin theta A. So the net reaction, net horizontal reaction on the tower will be T sin theta S minus T sin theta A. And the H is acting here upward, net 1. Net, I am telling net H. If the height of the tower is H, then the moment at the bottom of the tower will be H into H. So these things you please remember. Then another type of support, this is called gate pulley support, because there is a pulley over this one and the length, the cable runs over this one. So there will be a continuity on the cable actually. The same cable runs over this pulley and it is anchored here. So take another one, it is a saddle support actually. But there is a saddle with the wheel arrangement here, because this is free to move. This saddle is free to move over the tower. Okay, so what happens is this side of the cable is tied here, and this anchored cable is tied here also. So there is a discontinuity in the cable actually. So this will facilitate a small movement in horizontal direction. So the same way, so what happens is, because of this movement, the net horizontal reaction on the tower will be 0, because Ts sin theta s is equal to Ta sin theta a. This one, this is Ts sin theta a, this is Ts sin theta s, and the vertical reaction at top of the tower V is equal to Ts cos theta, same as before, Ts cos theta s plus Ta cos theta a. So horizontal reaction we have discussed actually Ts sin theta s and Ta sin theta a. So since the net horizontal reaction is 0, there will not be any bending moment at the bottom. Previous case there was a H, so it creates a bending moment. But here, because of the saddle movement, since it moves, your H will be 0, net H will be 0. So because of which there is not be any bending moment. So there are some problems. So let us go through that to to understand or to apply this what you have studied here. Thank you very much.